What if you could control not just what materials are made of, but how space itself is shaped around them? This is the idea behind Topotechnology, a growing and exciting area of research that blends physics, mathematics, and material science. Unlike nanotechnology, which manipulates particles and atoms, top technology manipulates topology, the geometrical and topological properties of physical systems. In simple terms, it means engineering how space is connected, not just what's inside it. But let's start with the question, what is topology? In math and physics, topology is the study of how objects are shaped and connected without focusing on exact distances or angles. A classic example is that a coffee mug and a donut are the same in topology. They both have one hole. Topotechnology takes this idea further by asking, what happens to physics if you design materials or systems based on these unusual topological features? Can you make electricity flow without resistance? Can you make particles immune to imperfections? The answer is yes, at least in some cases. One famous example comes from topological insulators, a kind of material where the inside is an electrical insulator, but the surface can conduct electricity perfectly, even if the surface is scratched or dirty. How is that possible? Because the electrons on the surface are locked in by the topology of the system. Their paths are protected by how the material's wave functions twist and turn through space. You can think of it like a mountain path that loops around a peak. No matter how bumpy it is, the path still connects the same points. Now imagine extending this idea much further. What if we could design not just materials, but entire spaces with custom topological features? That is the vision of Topotechnology. Scientists are now using ideas from topology to build metamaterials, structures engineered to have properties that natural materials don't have. These materials can bend light in strange ways, carry sound around corners, or create invisible zones where waves pass through undisturbed. A great example is the concept of topological photonics. In these systems, light travels along special paths that are protected from interference. Even if the material is damaged or irregular, the light keeps going like a train locked on a track. This could lead to ultra-stable optical circuits, quantum networks, or even light-based computers that are immune to tiny flaws that normally disrupt signals. Technology is also being explored in quantum computing. One of the most promising ideas involves topological qubits, quantum bits encoded in the braiding patterns of particles called anyons, which exist in two-dimensional materials. These braids are not easily disturbed, making topological qubits much more stable than conventional ones. This could be a huge breakthrough for building real, practical quantum computers. Let's ask another question. Is top technology only for electronics and quantum physics? No. It has applications in mechanics, acoustics, and even biological systems. For instance, researchers have made mechanical metamaterials that move in specific ways due to their topological design. You could build a sheet of material that curls itself up, folds in a programmed pattern, or protects certain motion paths from deformation just by how it's structured. So, what does the future hold? Top technology could one day allow us to create spaces where gravity, heat, or even time behaves differently, not by changing the fundamental laws of physics, but by changing how space is shaped. Some scientists believe that space itself might have topological properties at the quantum level, and by understanding these, we might gain new control over reality. Imagine materials that reshape themselves, or buildings that guide sound and temperature perfectly, or quantum systems that remain coherent forever. In short, top technology isn't about building things inside space. It's about engineering space itself, at least as it's experienced by waves, particles, and forces. From robust quantum devices to fault-proof circuits and responsive materials, top technology offers a new layer of design: shape over substance, connection over composition. Technology refers to the manipulation and engineering of topological properties in physical systems. properties that are invariant under smooth deformation, such as stretching or bending, but not tearing. It transcends traditional geometric control, focusing on global invariants like winding numbers, edge modes, or connectivity in materials, quantum fields, or even spacetime itself. Unlike nanotechnology or femtechnology, which operate at defined length scales, topotechnology operates across scales wherever topological order is relevant. It applies to materials, information, and fundamental physics, influencing how systems behave under constraints of symmetry, topology, and quantization. The core idea is that information and physical behavior can be encoded not in particles, but in the topologicals of space or fields. Topological insulators conduct electricity only along their edges, with bulk properties governed by topological invariants, like tying a knot in a rope. Its entire structure changes, even if you don't add or remove any material. Modern physics recognizes that topological properties can dictate physical behavior, especially in quantum systems. The discovery of phenomena like the quantum Hall effect and topological insulators revealed that topology governs robustness, protecting edge states from noise and disorder. These phases of matter are characterized by invariants, such as Chern numbers or Berry phases, which do not depend on local details. Topological phases remain stable, even under strong perturbations, making them ideal for error-resilient systems. Topological thus seeks to use these principles to engineer systems whose functionality is protected by mathematical structure, not just material composition. In a topological superconductor, the presence of Majorana modes at the ends of wires is guaranteed by the system's symmetry and topology, like the number of holes in a donut. It stays the same even if you squish or stretch it. Topotechnology enables the design of materials whose properties depend on global topological constraints, not just atomic arrangement. These include topological insulators, Weyl semimetals, and metamaterials with non-trivial phonon or photonic band structures. Such materials can guide electrons, light, or sound in ways that are immune to backscattering, defects, or imperfections. In photonics and acoustics, topological materials allow robust waveguides, edge-localized modes, and non-reciprocal transport. These features enable next-generation devices with low-loss transmission, topologically encoded memory, and unbreakable logic pathways. A photonic crystal designed with topological protection can route light around corners without scattering losses, like a river carved into terrain. It flows regardless of local bumps or rocks in its path. One of the most exciting frontiers of topotechnology is topological quantum computing, which uses anyons, exotic quasi-particles, whose braiding paths encode quantum information. In contrast to standard qubits, these systems store information in non-local topological states, making them intrinsically resistant to decoherence and noise. Computation occurs through the braiding of world lines, where the history of particle exchanges defines logic gates. The topological nature ensures that small perturbations do not alter the computational outcome, offering fault-tolerant quantum logic. This could lead to scalable, stable quantum architectures when suitable platforms like quantum Hall systems or major nanowires are realized. Microsoft's quantum research relies on topological qubits formed by manipulating major nanofermions in nanowires, like tying a knot whose function stays intact even if you shake the entire rope. In theoretical physics, space-time topology plays a central role in models of quantum gravity, wormholes, and cosmic censorship. In some approaches, like loop quantum gravity or topological field theory, spacetime itself is treated as a network of connected loops or surfaces, not a smooth continuum. Topological defects, such as cosmic strings or domain walls, can carry energy and information. Advanced topotechnology might involve modifying global space-time connectivity, possibly creating closed time-like curves, stable wormholes, or non-trivial manifolds. While speculative, such control would allow us to shape the universe not just geometrically, but logically. Some models suggest that information can escape black holes through topological transitions in the global structure of spacetime, like creating a shortcut through space not by digging a tunnel, but by rewiring the way locations are connected. Topological systems from DNA supercoiling to protein folding and membrane dynamics in cellular systems. Topological constraints regulate energy landscapes, determine entropic penalties, and control information flow. Topological defects in active matter, like cytoskeletal networks, can guide cell migration, tissue patterning, or morphogenesis. Future biotoptechnology could use engineered topological scaffolds to control biological development or repair, possibly without chemical signals. Topology-based control offers robust, scalable mechanisms for programming lifelike behavior. DNA topoisomerase enzymes regulate gene expression by adjusting the topology of DNA strands, like rethreading a tangled necklace without cutting it. Control through not. Topotechnology may extend to information science, where data is stored in topological configurations rather than binary states. Information could be embedded in entanglement networks, topological braids, or field configurations that are robust to local erasure. Such encoding could allow error-free memory and self-correcting computation, even under external disturbances. Topological encoding is especially useful in quantum systems where decoherence normally ruins fragile states. In classical systems, data patterns could be stored and accessed using nonlinear waveforms or knot-like patterns in electromagnetic fields. Braided anyons store information in their winding paths, not in individual particle states, like hiding a message in the way a ribbon is tied, not in the ink on the paper. Biological design principles are increasingly used in soft robotics, where compliant structures and materials behave in predictable, robust ways. Origami-based metamaterials, kirigami skins, and auxetic foams all rely on topological constraints to enable complex motion. These systems can store movement paths, protect against deformation, or translate local inputs into global Topological mechanisms are also used to stabilize walking, swimming, or climbing robots across variable terrain. This enables fail-safe behaviors in uncertain environments. A soft robotic arm can bend, twist, and grip using an origami structure with encoded mechanical responses, like folding a map so it automatically knows how to reshape itself when pulled. Culture technology challenges us to rethink the nature of control, where structure, not substance, becomes the primary lever of design. It aligns with a shift in science from material manipulation to pattern manipulation, from energy-driven control to geometry-driven resilience. This approach offers a unifying principle across quantum systems, condensed matter, biology, and even cosmology. The future of technology may not lie in building new materials, but in folding, braiding, and connecting what already exists in smarter ways. In this way, Topotechnology bridges mathematics, physics, and engineering at the deepest structural level. Rather than inventing a new material, a future device might reconfigure empty space to behave as if it were matter, like composing music not by choosing instruments, but by changing the way notes relate across time.